What up, what up? We got ourselves a doozy of a question here. Question 11, Math 100, Webwork 12. What a crazy, crazy question. This one's kind of tough. Let's read it. The upper right-hand corner of a piece of paper, 12 inches by 8 inches, and we got a nice little picture here, as in the figure, is folded over to the bottom edge. How would you fold it so as to minimize the length of the fold? That's why. In other words, how would you choose X to minimize Y? So how do you pick this thing? Like, where do you fold this thing so that this is a minimum? Well, it's not obvious. This isn't one of those ones where it's obvious. In fact, it's kind of hard to set up. So what my first thoughts are, I can do is Pythagorean theorem here and go like y squared is equal to x squared plus thing squared. But thing is not really a thing. I don't know what that thing is. And I would need it in terms of x if I was going to do my usual, set up your equation, take the derivative, set it equal to 0, solve for your critical points, blah, 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 right? You need that in terms of one variable. If you remember from the other optimization problems, that's what we do. Usually the thing you're trying to optimize, like volume of a cone, is expressed in two variables, and then you have to use something about the surface area to reduce it to one variable. Then you're set, you're right as rain, you take your derivative. From that point on, everything's kind of the same. So that's where we want to get to. So this one is, it's not obvious at all. So, what did I do? Well, oh, this is me, by the way, TallGuyTutoring. What did I do? Well, I friggin' went to GeoGEBRA and I spent friggin' hours trying to set this thing up because I'm new to GeoGEBRA, but frig, check this puppy out right here. So this is the problem, okay? So this is our sheet. It's 8 tall and then by 12. Okay, so see that there, 8 by 12 there. Oh, I think my face is in the way. There we go. Okay, so it's 12 long. And then it doesn't end here. That's not where it ends. It ends here. This green line, I'll show you why I had that green line there in a bit. So let's see if we can get some sort of extra info about this problem so that we can figure out an expression for this thing here. This is my y. Okay, this is the thing we're trying to minimize. So I guess, by the way, I'm not going to rush through this question. We're going to take our friggin' time because, I want you to understand everything there is to know about this problem and yeah, and how to do it so that you actually, get a little bit smarter about this stuff instead of just popping out the answer. Okay, so let's look at this thing. So look at this freaking beautiful thing. So as I move this point I, you have this triangle is a perfect copy of this triangle. How do I know? Well, look, this thing reads out the angles. This is 62.92, 62.92. As this moves, watch those two angles, they match. Wonderful, that's great. These two are 90-degree angles and they share a hypotenuse. So of course, they're not only similar triangles, they are congruent, meaning that's our math word that we use for it. The same. Congruent means the same. Okay, what else? Let's just understand the other parts of the graph here. This is x. I've chosen this to be x. That's my blue x there. This x here this is also x, right? Because remember, this is an exact copy of this triangle. This one kind of looks bigger, but that's an optical illusion. You can see the measurements on the side there. See, and they match at the different heights. They match, so that's good. Okay, great, cool. Who cares? Now this z thing, I don't know what z is right now, but I'm just going to call the top of this triangle z, and then since green triangle is the same as weird purple triangle, this is also z. All right, cool. Now, if this is x, what does this one have to be? That has to be 8 minus x, right? That's what's left over. That's x, that's 8 minus x. Guess what I can do? I can use Pythagorean theorem to solve for this green side. Maybe I'll need that, maybe I won't. I probably will. Okay, so yeah, that's all fine and good. Why am I doing that? Well, you know what? If I had z in terms of x, I would be right as rain because I can do Pythagorean theorem, y squared equals x squared plus z squared if z squared is in terms of x is in terms of one variable. That's kind of what I said before. Okay, so that's going to be our goal. That's the next goal. We're going to use some geometry to figure that out. But first, what I want to do is I want to actually try some, like moving this thing around and looking at what my y value does. Okay, so I can't get it like there. I think that's the smallest I can get it. It doesn't work, right? If you go here, you can't actually fold. You cannot actually fold the corner D down to here. So that's why there's no pictures being done. You have to be at least here at like 8 to be able to fold that down. If you folded it down, it would be a square there, right? Look at this, it's 10.84. Let's see what happens as I increase this thing. 10.54, 10.45, 10.41, 10.439. Oh, I almost F word. We're going back up. Look at that. Okay, so it started at near 11, I think. What did it start at? Okay, 10.78 goes down to 10.3 or 3, whatever, and then boom, back up. Okay, and then it's going to increase for the rest of the time until you get up to there. Okay, so there is a minimum somewhere. We're looking for that minimum. All right, so like I said before, not obvious at all how that works. Okay, now we're going to use triangles. All right, let's look at this triangle here and this one. Okay, these ones, they're similar. Similar meaning one is a scale model of the other one, but whenever you hear the word similar in math, it means the way you can think about it is an exact scale model. Okay, so like this is you have a small thing here and then like a big thing here. If they are similar and indeed similar, you can look at like one side length and say like, oh, this side length you need to multiply it by 2 to get the big one. That means all the side lengths you need to multiply by 2 to get to the big one. Okay. Anyway, so let's look first of all at AD. So look at this line AD and look at this line BC. Okay, and then look at this purple line cutting through. You see how that makes like a Z pattern? Well, here, follow this cursor. D to I to E to G or B. See that Z? Boom, boom, boom. You know what that means? That means the angles here, this angle and this angle have to be the same. Okay, not sure if that helps me, but something that does help me. This angle here has to be the same as this angle here. Okay? And what do you know? This angle contains a 90-degree angle and then something else. This angle here is also a 90-degree angle because this is a copy of this corner, right? A 90-degree angle. So this something has to be this something here. You see that? Once we have that, we're good. Why? Well, in a triangle, if you have two angles that are the same, you get, obviously the other one has to be the same because angles in a triangle add up to. So anyway, this angle, and then there's a 90-degree angle. This angle matches this angle, and then this is obviously a right angle triangle because it's in the corner. So as soon as we have that these two angles are the same as these two angles, we get that these two triangles are similar. Now, one thing that's important when you determine that triangles are similar is that you want to find out which sides correspond to which sides. Okay, there's a nice little handy trick. I never really did this when I was going through first year, but since I've been teaching, I've been definitely doing this, and it's just so much easier. So, okay, let's look at this. How do I get this naming? How do I get these names? This is notation for triangle IGE is similar to triangle ECF, meaning we got that there's scale model. Okay, so here's one way to do it. I'm gonna look at this triangle first. I'm gonna take the vertice connected to the 36.36, and I'm gonna go there to the 90-degree angle to the third angle. So I'm going to go IGE. I think that's what I did up here. IGE. Now I have to start at the same vertices and do the same thing. So I have to go the 36 to the 90. So in this one it would be ECF. Please say that's what I have. Yes, it's what I have. Okay. So now you can just match the sides. So like I to G is a color. I've made it a bright green. I just look to see EC, that has to be the same color. EC, that's the corresponding side. Okay, so really, if you took this triangle and you flipped it up so that it was sitting on this one, so take this corner and flip it up, then you would see that they're similar more clearly than right now. It's kind of confusing because one fell over. This one fell over. This poor bastard. This one, oh, and then we can read the other one. So GE has to be CF, so they have to have the same color. GE, CF, same color. Okay. Now, and then obviously the last side here, dark purple has to be dark purple here. And then we are good. So if we could, remember the whole reason we're trying to do this and looking at this different way is because we want to express Z as some as x's in terms of x's. If we can do that, then we can write y's as a function of just x, and then we're good. So let's do this. Let's do this. We want to use this side. We want to use dark purple and green. Why? Because this side, how long is this side? Right? We know how long that side is. I'm not telling you. Okay. So dark purple and green. In this one, it would be dark purple, which is x, and green, which is also in terms of x's. I don't know if I told you how I got that. Just use Pythagorean. Oh yeah, I did tell you. Okay. So you can do, if you're confused of what to do here, look up similar triangles or come to me. Send me an email. So you could do purple over green is equal to purple over green, and that's this thing. So z over 8 is purple over green, which better be x over this thing here, x over that thing there. Okay? Now, from this point, you know, hopefully you can see here how z's can be expressed in terms of x's. Once you see that, now you're off. That's the hard part of this problem, is seeing how to express this z thing in terms of x's. And from that point, it's the same as every other optimization problem you've ever done in your entire life. So hopefully that helps. Hopefully you appreciated that I didn't rush through. And the graph, I hope you guys like that, because it took me freaking forever to learn how to do this thing. But now I know for other questions, it's going to be freaking wicked. I'm going to make this graph available to you, okay? So it's on GeoGebra. Just download an app or whatever. It's a free app. The link is in the description, so go to the description, and then you can play around with it, and then you can look and see what the hell's going on with this thing. As always, if you want me to personally help you pass your course, click in the description, sign up to the newsletter. Okay, I'm going to be sending out emails, or just email me at TallGuyTutoring@gmail.com. I'd love to help you. You're all very smart. Keep working very hard. You're learning calculus. It's not easy. It's not a joke. Feel proud of what you've accomplished and keep working hard. And yeah, I think that's it. Hope you enjoy the video. Hope that helps. Okay, talk to you later.